Hi. So we're going to start talking about something called confidence intervals as a way to help us deal with the sampling variability problem that all statisticians have. If you remember, we talked about two friends who were randomly picking 30 people from this list of SAT scores. And if you look at all the green circles, that was the beginning of the sample from the first person who was pulling these SAT scores out of the population. And then all the black circles are some of the data points that resulted when the friend picked 30 people. And the problem these two people have, these friends have, you and your friend have, that is that you have different means for your samples. So it turns out we can build something called a confidence interval. And to do that, we're going to look specifically at this website down here that helps us to simulate what a confidence interval is. And then we'll learn how it's made. So I happen to have that link open. Just for reference, this link here with the green arrow is the SAT data if you are so inclined. So let's go to this website I mentioned. And here it is. A couple of things to notice when you first open it. If you look at the mouse, you'll see I'm hovering over the word proportions. We're going to want to change that to means. And it says Z with sigma. There's a bunch of options there, T and so forth. But we're going to use Z with sigma. What that means is you're going to do a one sample Z interval with a known population standard deviation. Okay, and so these things here are the parameters for the population. I just happen to know that the mean of all those SAT scores in that population is 633.37, and the standard deviation is about 87.3. Now, remember, the friends were picking samples of size 30, and what I'm going to do here is just set the number of intervals to 1. And if we click sample, oh, one more thing to notice. Notice down here is the word 95%. Make sure 95% is there because that's what we're going to do. If we click sample, we will see this vertical line here that's centered at the mean. You'll see this little green interval here. Over here on the right is the actual data points that the person got when they picked their sample. The mean of their particular sample, as you can see from the arrow, is 636.104. That's the standard deviation of the sample. We're going to ignore that for now. And this is what their data looked like. And then down below, here's the mean of their data. Now, because we talked about sampling variability, the friend can come along and they can pick a sample too. So if we click this sample button again, we're going to get a new sample. You'll notice that the green bar shifted over a little bit. That happened kind of quick. But you can see up here that the sample mean now is 644, and it was not that before. And what we can continue to do is keep clicking sample, and we'll see different little green bars. Now you'll notice this interval I just got is really pretty far to the left. It's centered here. If I click on it, I can see that it's centered at a mean of 607. We can see that up here on the top. We can also see it down below the graph here. And that interval runs from 576 to 639. So this person with this interval did capture the mean of 633. If I pick sample again, I'll get a different mean, and I can see this interval jump around a bit. Here's someone that, if I click on their distribution or their little confidence interval, it goes from 604 to 666. They too did capture the mean. Let's speed this up a little bit. Let's change that 1 to a 40. Now this is like 40 people all picking 30 people at a time from the population, calculating averages and getting these little confidence intervals. So let's hit enter or sample. Ooh, and something interesting happened. You'll notice that we have a bunch of green intervals and then this red one. And if you click on the red one, you'll notice that that interval starts at 553.045 and goes to 615.524 and does not capture the true population mean of 633. So this red interval represents one unlucky statistician working on their own. They made their interval, but their interval didn't capture the true mean. But all these other people with the green intervals are happy. You could see, for example, if I click on this one here, they had an interval that had kind of a high mean of 655. But there's also examples. If I look down near the bottom, if I click at this one, this person got a mean that was really low of 604. And if you notice, the upper bound of their interval is 635.51. So they just barely capture that 633. So the question is, how are these intervals built? It's actually pretty simple. Here's how you do them. They follow a basic format. This interval starts with your x bar always because that's what it's centered at. And we add and subtract something called z star times the standard deviation of x over the square root of n. So this part of it you should realize or recognize that's called the standard deviation of x bar, or the standard deviation of the sampling distribution. And when we're talking about confidence intervals, sometimes we call that SE. SE stands for standard error. Altogether, this thing altogether gets multiplied by this extra z star, whatever that is. This thing's called the ME, or the margin of error. Important statistical terms to know. And then here's your sample mean. Okay, well, we go back to you and your friend, right? Let's consider this first case here, this person over here. How would they build their confidence interval? Well, their x bar is 610, so they would have 610 first, plus or minus whatever this z star thing is, which we didn't talk about. And then, based on the formula, we need the standard deviation of x over the square root of n. Well, we know the denominator is the square root of 30 because we pick 30 people at a time. And if we go back to that website and look at it, you'll notice over here, I'll click with my mouse, we had a standard deviation of 87.3. So that's what's going to go in here, 87.3. And then finally, how do you get z star? Well, if you remember back on the website, I told you just real quickly to make sure that the confidence level was at 95%. And so that actually has to do with something called the 68, 95, 99.7 rule, which you may remember. And one of the consequences of that rule is that if you want to capture the middle 0.95 or 95% of data, then you have to go from the mean down 2 standard deviations up to 2 standard deviations above. And if you do that, you will capture the middle 95% of data. So z star is the z-score you need to capture the percent of data that you want to capture. In this case, we want a 95% confidence interval. So we're going to do 610 plus or minus 2 times 87.3, because 2 is exactly the number of standard deviations I need to go left and right of the mean to capture the middle 95% of data. That interval will turn out to be the following. So we'll go to a maximum value of 641.88. Oh, my 1 didn't write there. Sorry, that's 641.888, or 88, that is. And then it goes down to 578.12. So this is the first person's confidence interval. And so they're 95% confident that they've captured the true mean somewhere between these numbers. Now we have the advantage in this case of knowing the true mean. I mentioned to you on the other web page that it's 633. Oops, error there, sorry. It is 633.37, which is indeed in the interval. Now let's see how the friend did. The friend was working on their own, and when they did their confidence interval, they got an x bar, here it is, of 620.33. So let's go write their interval out, 620.33 plus or minus 2 times 87.3 over the square root of 30. And it just so happens that the upper and lower bound for that interval are 652.21, and it goes down to 588.45. So this person would say they're 95% confident that the true mean is somewhere between 588.45 and 652.21. And again, this person also captured the true mean, which was 633.37. And if we continue to make intervals this way using a z star equal to 2, call this z star, then it turns out that for the different values of x bar that the different friends may get, that about 95% of all the intervals that this group of friends create will end up capturing the true mean of 633.37. So it turns out to some pretty special sentences that you should know. So let me just show you those now. So here they are. We can say something like the 95% confidence interval for our data for the average SAT score of Jericho seniors is from blank to blank. And that's going to vary from sample to sample, as we've talked about. We can also say that we're 95% confident that the true average math SAT score of students at Jericho is between blank and blank. And finally, I guess the most complete way to state what this is that 95% of the possible samples will produce confidence intervals that contain the true average SAT math score of all the Jericho seniors. And so that also means that 5% won't capture them. And so to finish off, if we go back to that web page where we were simulating confidence intervals, you'll notice down here, where my mouse is down on the lower right screen, it says intervals containing mu, 39 out of 40, and underneath it, it says a running total of 50 out of 51, and that says 98%. So 98% of the intervals we've created so far have captured the true mean. Well, if I start hitting this sample button up here a whole bunch of times, you can watch this running total down here below change. And notice how it's hovering around 96% now, going down a little bit, 95.6, 95.7, and so forth. And we've done 1,131 intervals so far. If we did many, many intervals for a really long time, what we'd find out is that this running total would zoom in around 95%. And that's because we used a z-score of 2, which would capture the true mean 95% of the time. And that's your basic introduction to one sample z intervals. Thank you for watching.